Okay, so I'll just briefly introduce myself so you know who I am. But I'm the CEO and co-founder for Neuron Innovations, and I'm just strategic lead for Project Blueprint. I've helped put this project together. We helped, our team went and managed to pull in all the consortium members to make this work. And our role in this is the project lead organisation. We've built a public services network, and in this particular use case, we're looking at surveillance data, integrating surveillance data, and making it a public asset for anyone. We've got some excellent partners here in Drone Cloud, ANRA Technologies, Cranfield Airport, Distributed Avionics, Skydrone's Ebony, Future Aerial, University of Southampton, and Cranfield University. We brought together a team of people to go and make sure that we can go and fill in all of the different gaps that we needed. Now, just giving you a quick problem summary. You may have come to the launch event we had about a year ago now, but I'm really just summarising and skipping over this again. The main problem is there's really a lack of suitable DAA solutions, which is limiting the BVLOS operations to TDA trials. So general aviation are getting quite fed up with all these TDAs popping up everywhere. And a temporary danger area, you can't build a business model around temporary airspace. Businesses need to be able to run for years at a time to be able to actually generate sufficient revenue to actually make that money back. And so generally building your operations around temporary airspace just isn't a long-term or sustainable solution. UTM services are required to mitigate the risks, but there wasn't really a currently implemented MVP for how UTM works. How do you bring in all of these different UTM providers and make them interoperate with each other? And that's what we've tried to do here. Now, when it comes to sort of detecting the void and sensing, there's a range of different solutions out there, from EC, which is electronic conspicuity. So these are transponders on board planes that will tell you their position, and there's a long list of those. We've got radar solutions that are essentially emitting a beam and letting it reflect from the aircraft to be able to tell its position. And you've got EO, which is electro-optical. These are like things like cameras, onboard cameras, using video cameras to be able to see where the other aircraft are. Now, EO is not good. It's very difficult to assure that, because you could have a bug stick to the camera lens, for example. And will it work at large distances? Well, the solutions we've seen out there show that most of them don't. In terms of radar, will it fit on small drones, and is it affordable to scale? Currently not. And the problem with EC is, well, does it work without airspace change? And the answer is no. But which of those solutions did we pick? Well, we felt that electronic conspicuity was the right way to approach this. We need to be able to see each other, and starting off from a point of everyone emitting their position is probably the best way to do this, rather than starting from a point of non-detectability. Let's start with aircraft pushing out their position to other airspace users, and we can all then integrate safely. That does come with some challenges, so we'll come on to those a bit later. So our approach really was a cooperative approach, using electronic conspicuity to detecting the void, which was enabled by transponder mandatory zones, in line with the DFT roadmap, and using ADS-B networks and UTM and ATM services to mitigate those risks. So we deploy a low-altitude TMZ, try and keep it at low altitude so it doesn't disrupt too many other airspace users. We deploy the ADS-B network to be able to pick up all of the other aircraft. We integrate those systems with UTM services, and we can come onto the UTM side in a moment. We test it, and then we scale those systems across the UK. And the aim of this project is to develop the minimum viable product that can evolve over time, but get that those first operations underway, and we can then develop from there. So in terms of what that looks like from a team structure, we have 2 operators in Future Aerial and University of Southampton. We have 2 ground control stations, or flight control. It's essentially the avionics that the drones use to operate in Skydrones and Distributed Avionics. We then have 2 UTMSPs, or 2 unmanned traffic management service providers in Drone Cloud, acting as both. We then have the flight information display in CIS, which is like the interface with the airport, and also providing the interoperability between the UTM instances. in ANRA Technologies. And then we have an ANSP and ATC in Cranfield Airport. And we as Neuron are providing the ground-based sensor network that was feeding into all of these different systems. We then have Cranfield University working on the onboard detect and avoid, and also looking at the flight information display verification. We've got Eb and I, who've done a huge amount of work on the safety assurance processes. And we have the University of Southampton also looking at ground risk using their modelling services.
So today we've got the Blueprint launch event at Cranfield Universities DARTeC Centre. And this event is bringing together 10 different consortium partners to showcase the progress that we've made as part of the Blueprint project. Blueprint project is all about enabling beyond visual line of sight drone operations. What we've seen in the past is a lot of trials in trial airspace or temporary danger areas, but now we're trying to move towards a more integrated airspace with transponder mandatory zones, TMZs, and ground-based ADS-B networks. So we're showing how these systems interact and integrate into UTM systems, into ground control stations, and how drone operators can use that technology to enable beyond visual line of sight operations.
So we're now going to show you a demo, and the scenario is a small multi-rotor drone is being tasked to complete some inspection flights beyond visual line of sight of the pilot within this TMZ. And the first stage is that they need to obtain approval to fly. So we're going to quickly take you through that process.
Here you can see Skylos Cloud web application. Also, you can see it's 3D mission planning. So an operator can see the mission from different angle, from different view.
The first thing the user needs to do is import the mission from the SkyDrones library. The systems are already been through. In our platform then, the user will actually then add a mission name. They will put in an ID and also the autopilot or pilot ID as well. So the IDs that will then be validated against the registration service. And then the final thing is, because we are operating in the airport environment, the system notifies the user that they have to request airport approval. So they hit that button, and then it should be sent to ANRA system.
The information that arrives to the airport is not just the operational volume or the geometry of the operation, but also an extended flight plan about who the operator is, what vehicle they're going to be flying, and in what mode, which all helps the actors decide on whether to approve the operation or not.
Okay, we've just seen how the drone operator will plan their flight in their GCS, how that will be deconflict from other flights in their UTM, and how they obtain airport approval within the airport interface. For the next part, we're going to be doing some live flights. So the drone will take off, fly around within this TMZ scenario, and we'll put another aircraft, simulated aircraft, on a collision course with the live drone, so that we'll show you how the remote pilot will avoid this collision.
What they'll be doing is looking over the aircraft, doing some basic airworthiness checks, making sure that there's no cracks in the propellers, cracks in the aircraft, landing legs. The aircraft, I think it's now taken off. So this is one of the actual problems. One of the big problems with ADS-B that needs to be solved is around what data you use. And so this has been actually one of the good challenges that we found as part of this project, is how do we use a common data. The pilot should now start the deconfliction routine fairly shortly. So they will start seeing the aircraft coming into the ATZ. And you can see now it's flying straight towards the other aircraft. So what will be happening is that aircraft will be visible on the drone pilot's ground control station. And hopefully what we'll see is the drone coming into land. And I think it has already landed. So So the drone is now on the ground and collision has been averted. Thank God for that. So yeah, it's just showing how a deconfliction would happen. It's certainly safe, it's certainly out of the way, and the aircraft is now flying over, but the drone is coming to land and the collision has been averted. So we're just showing there how an aircraft can be detected, how two aircraft can both be tracked within 4 pieces of software.
So there you've seen what we presented 12 months ago, and I'm really excited to show you what we're about to present to you today. You're probably all aware of the TRA policy concept that came out just before, actually, we presented that to you last year. And we're certainly now well into that accommodation phase. How do we make a DAA sort of capable of deconflicting aircraft? And how do we use TRAs as a means to be able to do that? How do we generate an open UTM ecosystem where everyone can participate? That's some of the questions that we're going to hopefully answer today. In terms of that roadmap, well, what have we done so far? We've developed the requirements and architecture. We helped co-found the Shared Airspace Council. We've installed modeled the initial sensor network and built prototypes, integrated systems, and conducted the testing. And we applied to the CAA TRA sandbox, and that was just before that launch event you've just seen. Since then, we've got accepted into the CAA TRA sandbox. We've enhanced the sensor network. We've developed traffic alerting systems. And we then developed and tested the MVP systems for the UTMs, integrated them all. And we've had the TRA OSC now approved for operations. So we haven't yet got TRA yet. Is there anything missing? So we'll come on at the end. What we'll show you is what's going to happen over the next 9 months. But we have got the TRA OSC approved. And so the TRA is now the last part of the puzzle, along with the assurance. So we'll now kick off the presentations. And so today what we'll be talking about is some of the airspace change. We'll look into the CIS to ATM interface, flight information display verification, ADSB network and modeling around that, ground risk modeling, UTM services, GCS integrations, and non-cooperative detect and avoid, finished by the safety assurance process. We'll then kick off into the live demonstrations. So let's start with the airspace blueprint. So if we look at the different air risk classifications, when we're first of all looking at initial airspace risk, we generally have, it's ARC A to D. We're going to ignore D for now because it's very complicated. But ARC A to C are really where most of us are going to be focusing on in terms of operations, unless you're flying very, very big drones in things like Class A airspace. Now, you've got ARC A, you might be familiar with something called atypical airspace. ARC A is atypical airspace. And the level of tactical mitigation you require increases as you get further away from objects. If you're flying, if you're literally landed on someone's roof, then you're not going to cause any risk to other airspace users. If you're 10 meters away from someone's roof, a little bit, maybe a tiny bit of air risk. If you're 100 meters away, then yeah, a sizable amount of air risk. So the amount of risk that you pose to other airspace users increases as you get further away from objects. So there is this sort of band, which, as I say, ramps up in terms of risk, where you have this ARC A airspace, where DAA, as defined by the CAA, is not required, but some form of tactical mitigation is required. Once you get out of that, we believe the magic number is 250 feet. In terms of what that actually is. There's a reason for that. In ASTM, you need 250 feet of vertical separation, and aircraft, except for in some very specific circumstances, can't fly within 500 feet of congested area or people and property. So there is a clear, if you're looking for 250 feet separation, then flying below 250 feet, I think that the definition really, I don't think ARC A airspace can really say that it's any higher than 250 feet. Certainly not always 250 feet, but it's not going to be higher than 250 feet. ARC B and C airspace depends on what class of airspace you're in, and also whether you're above a congested area or not. If you're above an area that's quite nice for landing, for example, like a field,
then you certainly couldn't say that it's atypical in the middle of a field, especially if it's a runway. So certainly, when you're flying objects and structures, then ARC-8 airspace has a big place, I think role to play. Really, what are we looking at in here? We're looking at ARC B and C, but also a lot of these systems are useful for this ARC-A tactical mitigation. So they're certainly not separate, but we want to cover really all three of those types of airspace risk classifications. So the vision really is that we've got these different types of TMZs. You've got TMZs that might be around an airport, like an ATZ, and you've got TMZs that might be in Class G airspace, for example, or not outside of an ATZ in Class G. Now we do believe that there's some differences here. If you're flying in Class G airspace outside of an ATZ, then the ATZ, the airport is unlikely to have as many resources available to that airspace. So there needs to be other systems in place. Now, what do the proposed requirements for a TRA or a TMZ? Well, you kind of have two types of airspace. You have controlled or managed, let's call it that. Things like ATZs, things like Class C or D airspace, or IFR approaches. There is a conspicuity requirement, should be a conspicuity requirement for all of these TRAs or TMZs, certainly within the blueprint that we've put together. There needs to be UTM interoperability services within these. There needs to be the ability to activate or deactivate and put restrictions in place by an ANSP within these TRAs and TMZs. There needs to be some form of traffic information service provided by an ANSP within these TMZs. And there needs to be a detect and avoid service provided by an SDSP or whatever else you want to call it within for the operators. And there's a range of stuff. The CAA pulled out this policy concept, DAA policy concept now, that basically builds on what JARIS and ASTM have provided in those links you can see there. The main difference really between that controlled or managed airspace and uncontrolled or unmanaged is that, as we've found out, these things are generally far away from airports. So airports probably don't have much infrastructure in place around those. So what is that service that's provided by the ANSP? Now, I think some people in this room, probably we're still in this debate about what that service looks like. And I'm sure there's things like open air that may solve some of these questions. We believe that it should be some form of basic service, not a full-blown traffic information service that you would expect in an airport, but maybe a traffic information service light or something like this. But let's call it a basic service for now. And that's basically what we believe from a blueprint perspective is needed. Now, I talked about conspicuity, and if you see in this previous slide, I put conspicuity in hyphens for a reason. I didn't use the word electronic there, because there are multiple types of making yourself conspicuous to other airspace users, not just electronic means. Now, there are three proposed ways of complying with conspicuity. And the reason for that is because we need to incorporate all airspace users, not just those who can fit electronic means to their aircraft. So the thought process here is around, well, you can have a strategic only flight plan, for example. So say if you are a model aircraft and you're flying at a model aircraft club, then you could put a flight plan or essentially an area around your operation, and you don't need to fit ADS-B to your aircraft if you're flying there. We need to be able to account for model FPV flyers, drone flyers, or visual line of sight, Mavic pilots. We can't, if we expect all model aircraft and recreational drone pilots to fit ADS-B to their aircraft, the plan's not going to go anywhere. So we need to be able to account for these guys. And we believe a strategic-only approach for them is certainly good enough. We've then got two other types, which is an onboard ADS-B, and that could be 1090 or 978 megahertz. That's in line with what the DFT is recommending and the CAA is recommending through their policy. And these things called ground beacons, which is basically ADS-B on the ground. It's essentially broadcasting a position. Say if you've got paragliders, for example, who want to fly up and down a cliff, then you could put a beacon there to notify other people that that's happening. So these are the kind of three: onboard, ground-based beacon, or a strategic plan. And if you do that, you're not going to make everyone happy, but I think you can actually make a technical solution work. You can see some examples on what that might look like in a real-life situation. So in terms of the airspace change we've been working on, Cranfield Airport ANSP have been leading an airspace change proposal for the TRA. And the TRA is matching the existing ATZ volume, but it's also got this big area across Milton Keynes and the application was submitted a while ago now. The University of Southampton OSC has now been approved, and Cranfield are about to kick off that TRA process with the CAA. So there is probably some time left to be able to go and get that over the line, but the OSC being approved is a good sign that the rest is almost a formality. And at that point, I'll hand over to Akshav, who will talk about the CIS and ATM interface. Thank you.
Thank you, James. Hi, everyone. My name is Akshav. I'm the technical project manager for Blueprint at ADNRA. What we're trying to do here is we are a common information service provider for Blueprint, and we're providing the solution of a TC platform, which allows the ANSP to accept, reject, and amend flight plans. So what do we do at ANRA? So at ANRA, we develop software solutions, modular software solutions, that to safely integrate and implement drone operation in the UK airspace. And we've taken part of several projects, DASA, Future Flight Challenge, such as AMILED, and also CESAR projects. We're based in Washington, DC, New Delhi, and also in London, as well as in Europe. So to discuss the interoperability in Blueprint, what we're trying to do here is we're building a scalable, secure, and flexible framework, right? And these are the characteristics that our platform includes, right? So we're including a cloud-based service so that people can, or actors, can actually connect to our system via open API and connect to our system via a collaborative system. We have multiple provider support, so seamless communication, and we are mostly focused on the open access framework that enables aerodromes and UTM services to collaborate peer-to-peer basis. We also have a secure communication. If you think about it, as an ATC platform, security is very important. And we also have data exchange support relating to flight authorization, traffic information service, geo-awareness, and also flight intent conformance monitoring. Right. So here's architecture of the Open UTM architecture itself. So this was the initial architecture at the beginning. Here you can see different actors, the operator, the UTMSP, as well as ANRA. The UTMSP is responsible to send the flight plan to us, and as a common information service provider, we'll process that data and send it to the air traffic controllers. Here, I think an important thing to mention is that if a flight plan is coming through our system and that flight plan is intersecting with a specific control zone, that control zone will be the only one receiving the flight plan. And the reason why we do this is because if you think from an air traffic controller point of view, having the right information in front of you is very important. So we try to dedicate that information that's coming through the UTMSP and send it to the proper air traffic controller. So this is our solution, or our MVP. This is the ATC UI. So in the ATC UI is divided into two. We have the strategic side and the tactical side. In the strategic side, we incorporate extended ICAO standard flight plan, which allows the ATCO to receive an additional information of the operation. That will include call sign, if you have an ADSB transponder, and your location. Also, we use a digital flight strip format, as you can see, and you will show all the different characteristics of that operation, as well as the different status. Also, you have a strategic and pre-tactical awareness, so you could select the flight strip and see the operation on the screen, on the map over there. And we have three approval states. So we have accepting, so you accepted your flight plan, the ATCO accepts the flight plan. You have a rejection, and you have amendment. So let's say you have an operation which the ATCO receives, and they want you, or they want that operation to enter that airspace at a specific time, the ATCO will have the flexibility to amend the flight plan and tell it when to enter the control zone. And here you have a lot of functionalities, which you will see in the demo. So this is the tactical UI. So the tactical UI provides an overall situation awareness of the traffic. This concept was based on the two configuration controller. So you have the strategic side and the tactical side. In the situational awareness, you have Neuron ADSB feed, as well as UTM telemetry that's coming from Drone Cloud. Our data are fused, meaning that if you have data coming from telemetry and ADSB, our fusion service would fuse that data to give you the most accurate position. We have altitude correction, getting the data from a METAR and correcting the altitude to the elevation of the airport, or QNH. Also, we provide UTM traffic service, so we track and we identify. We have different set of filters as well, where you could see the airspace layer, the control zone, which you will see in the demo later. And that's pretty much it from me. Thank you so much.
Hello, I'm Christantus from Cranfield University. So what I'm presenting today is about the verification we did for the ATC UI from ANRA. So what we did first, before the verification at the beginning of the project, was we negotiated with ANRA to define some requirements for the ATC UI. So what we went further by discussing with the air traffic controllers from Cranfield Airport to ascertain what they require the ATC UI to look like, because they will be the primary users of the system. So we divided those requirements into 3 core parts: the user requirement, the functional requirements, and the non-functional requirements. So during our discussions, we spoke about things like the general system requirement, the display, how they would like to see the display. Would they prefer one display for the strategic and the tactical phase? And it's based on that conversation that we agreed on splitting it, and that's why from the ATC UI that ANRA demonstrated, you had different interface for the strategic and tactical. So we discussed, after this discussion, we came up with this requirement, and then ANRA went to develop the system. When they completed the system, we defined scenarios which we used to verify this system. So the first thing we did was to look at the blueprint CONOPS, what blueprints intended to achieve. And then we came up with these 5 main scenarios, which is having a drone operation inside the FRZ, having another crossing the FRZ, having one in the FRZ and outside the FRZ. So these scenarios are all scenarios relating to the blueprint project. And once we define that, we try to run the ATC UI to see how these particular scenarios would appear on the ATC UI. So when we did that, of course, we had our requirement documents, which we are matching. So for each requirement, we check if the ATC UI had satisfied it. And then for us to do that, we also did not do a live demo to test the system. So what we did was we integrated the ANRA ATC UI into the simulation environment at Cranfield University. And we understood that the ATCO would be looking at 2 screens. So one screen would be the normal ATC screen, which he already has, and possibly now the ATC UI, which is an additional screen for the UTM services. So we made the simulation environment to be such that you have an ATCO looking at both screens. So we provided both screens. And then we invited some people, because one of the requirements was that the ATC UI should be something that will be easy to use. So we don't want the ATCO to have to undergo additional trainings. So we invited some people, which we gave them a training for an hour, and we asked them to look at these screens and then see if it's something that they can use. Those people have just basic knowledge about operations, flight operations. So at the end of the day, we're able to match with our system requirements. And when we finished running those exercises with those guests, we asked them some questions. We developed some questionnaire for testing the user experience, how they experience the system. And we also got a standard workload assessment template, which we also applied to them. And at the end of the day, most of them were actually happy with the system based on the results there. It wasn't 100%, but it's a system that we believe that could still be developed as time goes on.
Hi guys, I'm Jan Dabrowski, CEO and co-founder of Drone Cloud. Yeah, it's a pleasure to explain to you a little bit more about, I guess, our contribution to the project. So, who and what are we as Drone Cloud? So, I guess it kind of will have been obvious by now that we're a UTM service provider in the context of Project Blueprint. But I guess one of the things that we've brought to the project, and I guess that, we want to kind of take forward, is our existing customer base and the flight management platform that we have today, and through, I guess, that kind of unification of the existing customer base that we have, the flight management platform that we have today that helps pilots and organisations manage their overall fleet compliance and I guess kind of compliance with regulation. That really gives us the ability to bring into the project a view of what are we actually, what are we trying to achieve from UTM services, but I guess the entire kind of packaging those services up and making them usable and accessible by end users. So as much as developing the UTM services for the project, we've tried to really kind of bring in that customer experience and ultimately the end exploitation element of it. So making it all worthwhile, you might say. What we've delivered specifically for the project is, I guess, two main things. So we've delivered UTM services, and I'll kind of go through those in a second. But we've also then been part of that integration piece, and I guess the open integration part of it is critical. You might have seen on one of the previous slides two UTM service providers. That's something that's really, for us anyway, selfishly, we think is a real kind of unique part of this project, in that we've genuinely delivered a multi-UTM service provider via an open access framework capability as a consortium. Initially, there was another UTM service provider, but then we took over that. I won't go into the whys and wherefores for that, but we did, and it works. But really, the point that we're proving there is that we've enabled that synchronization and discovery service as part of the integrations. I'll get to that in a second. But so from a services perspective, we created operational intent volumes, so both laterally and temporally. We'll see a lot more of that in the demo later. We also provided conformance monitoring. That's really, I guess, a key part. So it's all well and good creating a volume that we're intending to carry out our operations in, but we need to make sure that we're conforming to that. And we've done that, and we've done everything, I guess, as a consortium, wherever possible, applying rule sets or standards that are open and available to us. So in this case, heavy kind of influence from ASTM. We also provided a flight authorization service, not from a USP service provider perspective, so not to be confused with the stuff that the ANRA guys have been doing. But I guess this is the sort of front end to that service. And we've also provided the geo-awareness service, again, from a kind of end user perspective. So bringing in those elements that are really critical to an operator carrying out a safe operation. In terms of the integrations, so I kind of mentioned that in my kind of getting to this stage, but the discovery and synchronization service, that's been really key to us. I can't really overestimate or should we say overplay that part of it. Certainly for us, that's a real key USP on this project. It's something I'll get onto it in a second. This is the good side of it. There's bits that are missing that we need as an industry going forward. I'll get to that in a second. But certainly from an interoperability perspective, it's been really good to see that working. The other integrations, air traffic management. So again, that operator entry point into what ANRA were explaining in terms of the airport authorization service there. And then the traffic information service, so bringing that in a way that is useful and accessible to operators. Our friends at Future Aerial and Southampton Uni. And also integration of ground control station. I think this is something that's kind of often overlooked. Certainly when we look at GCS or ground control stations in a kind of local context, but that is going to be increasingly moving into a cloud-based capability. And I think that's been really good that we've managed to demonstrate both the local and the cloud-based control of UAVs as part of this project. So I think, yeah, in terms of delivery, it's been great. This is just a quick, I'm not going to go in service by service here. I think that would kill you all, but it's really a bit of a drone cloud-centric view of the project, but ultimately showing that you've got per UTM service provider there. All of these services that we're talking about, they are just services, call them services or features. They need to be packaged together into an accessible platform. And again, kind of reiterating what we feel like we've brought to the project. It's enabling end users to actually access those UTM services in a way that is appropriate and relevant to them. So really, I guess, a kind of a hub of all of those services feeding in and communicating, importantly, with that CIS or Common Information Services layer. There we go. There's going to be some videos. I'll kind of talk through them, so try and make it kind of... Well, there's no music as far as I'm aware, so, and I'm not going to sing or dance or anything like that. Right, so this, not to steal the thunder of the demo, but equally, if it all goes a little bit wrong, there's you saw it here, and this is it working. But it won't go wrong. It will be absolutely perfect. So here we're just really, I guess, I mean, this is part of that integration of the GCS there. So you can see that we're pulling in an operational area or kind of intended flight area from a GCS, in this case, Skydrone's cloud. So I mentioned that kind of cloud integration. And then you've got really, I guess, quite a simple process of defining that operational area. So you can see here, that's the temporal part. So when is the operational area going to be live? And then the lateral, so that's the horizontal and vertical buffers. So when we create the operational intent volumes, that's the flight geography plus the contingency volume around it. And then you can see that that's effectively all of the waypoints have been sent to the UTM to create that operational intent volume. And that's, kind of, I guess, a visual cue for the operator there that that's been done. And then you can see that the live telemetry from the aircraft is then being shown to the operator there so that they know ultimately where they are. And then they'll also be able to track themselves in terms of whether they're conforming. You can see that the OIV has been saved now to the UTM. And the mouse is nicely showing it. I'll go on to the next video. There we go. We're just kind of showing the stages, I guess, kind of building up an operation here. So what we'll be doing here is, in a second, we'll be... let me just check that's not the same one. 1 second. Here we go. Submission and authorization. Right, so that was replaying the same one. Apologies for that. Right, so the operational intent volume is in the UTM, so it's kind of ready to have ultimately something done with it. And this is, I guess, that bit where the interoperability comes in, and also the integration with ANRA. So that operational intent volume has been sent to the airport or to the ATCO, and the ATCO has now reviewed and approved it. That was all pretty quick. You'll see more of this in the demo. But there you can see that flight plan has been approved and cleared to proceed. So just to kind of give a quick sneak preview of how this will happen, you can see here that we've tried to launch a little bit early, so you get a visual cue to say, it's not time. So again, it's the temporal part as well as the lateral deconfliction. I'm clicking right, and it's not quite going right for me. Here we go. Right, in flight. So here we go. So we've been cleared to proceed. So the ATCO has had the operation, approved it. And what we'll do now is we'll start the live traffic and also the data coming in from Neuron. Again, another integration there, so you can see other aircraft in the area. And just to kind of prove, I guess, that concept of the OIV or operational intent volume conformance here, we'll start a mission, and then we'll control that by the little kind of joypad on the right-hand side. But again, you'll see all this properly live in the demo a bit later. And you can see that the aircraft telemetry is coming in, and the aircraft is currently conformant. It's doing what it was intended to, but you can see that we're intentionally about to send it outside of its operational intent volume. So you can see the aircraft is green at the moment, so that's signifying that all is okay. This is also, by the way, visible from the ATCO side as well, but the operator's got a nice visual cue there that I'm green, I'm okay. In a second, there you go, you can see that for the prescribed period, and again, according to all the ASTM standards, we've applied a prescribed period of being outside the OIV, at which point the aircraft is no longer conforming, and we put effectively an emergency bubble around that. So you can see that red volume there, effectively just alerting the operator, but any other operator from another UTM service provider, they'll also be getting that same information. And they can see that there's something that is non-conforming, and they should take potentially corrective action, or the ATCO could effectively enforce corrective action. So we're just showing that you can come outside of an operational intent volume, and as long as you come back in within your threshold, that you can then become conformant again. If you stay outside, as you can see we're doing now, you'll go from orange, which means I'm effectively non-conforming, but I have the ability to come back inside my operational parameters and continue conforming. If you stay outside for a sufficient period of time, you'll see that still with the emergency perimeter around it, it will go red in a second, meaning that it's no longer conforming and it can no longer become, no longer can return to a conformant state. And there you can see there that there's an off-nominal volume created around it. That everyone now needs to be aware that there is an aircraft that is not behaving, and corrective action needs to be taken. So that's kind of a bit of a, in a nutshell, what's going to be in the demo later, but with multiple scenarios. So hopefully James not stealing too much thunder, but again, a nice, you saw it here, but it will all work on the day. Right, let's see. I seem to need to click several times to get off. There we go. Right, so just to kind of start wrapping up then, again, reiterating that from a drone cloud perspective, we created the services with and the integrations with the rest of the consortium, but we have what we think is quite a kind of, if not unique, but quite a privileged position in terms of being able to then really package that directly into a platform and an application that is accessible to end users. So ultimately, we have a commercially viable route to deploying these services, which I think is really key. Quick one to completely wrap up on my side. So in terms of learnings and takeaways, so UTM services need packaging to be accessible to end users. Hopefully we've kind of demonstrated that. So the services in and of themselves, they're all key to delivering a capability, but unless we package them in an accessible way, it's hard for end users to derive value out of them. Open access UTM enables UTM to scale across multiple UTM service providers. I think we've proven that, and that's a big tick in the box. But as a consortium, we've proven it can be done, but there is a but, and that is we've effectively delivered as part of the consortium a proto CIS or Common Information Services layer in the kind of open standards language. That's an open UTM services layer. We've delivered that for the purposes of effectively delivering the project and proving the capability. But that's something that we see as in terms of a follow-on next step. And we've got some of us in the room now are actively working on this. You all know who you are. But we really need to effectively move to that next level around creating let's say a nationally agreed open UTM services layer, aka CIS layer, that we can all agree on and ultimately all use to, I guess, really deploy what we've delivered in Blueprint and actually start commercially exploiting it. So that's it from me. Thank you very much.
Great, thanks, Jan. So I'll now talk a little bit about traffic information. We've talked about the UTM services, both what that looks like from an airport perspective, what that looks like from a drone perspective, drone operator's perspective, and how that kind of integrates. How do we see that? But these things don't, they need data for them to work. An empty screen doesn't tell you anything. And that's where you need traffic. So really what our aim in this project was to build a recognized air traffic environment that could feed these DAA and flight information display systems. And we wanted a few qualities to that. We wanted predictable coverage down to low altitude, so around about 200 feet. We wanted multiple eyes on target. When I mean eyes on target, I mean we don't want to be relying on one sensor to see each aircraft. Because one, it has no redundancy in the system, so you have to start going through high levels of assurance on those single systems. And you don't get any spoof resistance in ADS-B without them. You need at least two ADS-B sensors to have any kind of spoof resistance, ideally 3, if not 4 sensors to have spoof resistance, which increases the security of the system. We need it to meet assurance requirements, which we now have, albeit 6 weeks ago. So that allows us to kind of move to the next phase of the project. We wanted to be sensor agnostic and software agnostic. We believe that any ecosystem needs every sensor to be able to be integrated. We need every software to be able to integrate into this ecosystem. So we wanted to keep it open on both sides. Initially, we wanted to focus on pilot-initiated avoidance. This is from, at the bottom, you can see this from Jarasora Annex H, which talks about the different stages of a detect and avoid system, right, from sensors to surveillance data processing to the actual tracking of aircraft, the monitoring and alerting, and then the actual operator. We wanted to have the operator in the loop because we believe that that's the first step in the MVP. Later, the operator will reduce their responsibilities, and a lot of that avoidance will become automated, or certainly automatic, if there's any members of the CIA here. What we're looking at here are the different stages, and we're doing pilot-initiated avoidance at this stage. So what is the neuron network? What have we built here? Well, I think it's now the first public surveillance network that's out there where users can access raw data directly from sensors. I don't believe there's one like it elsewhere. I think ultimately, when I say public, what do I mean by public? I mean, well, it's open source, it's permissionless, you don't have to come to us to access it. We can't stop you from accessing it. It's sensor agnostic, so you can integrate your own sensors into it. If you're a different sensor provider, you could integrate your sensors into it without any problem. And anyone can access it if you pay them for it. The person who owns the sensor, put it that way. It's serverless, so there's no central point of failure in the system. If I've got a detect and avoid system, I can access the sensors that I want to access. We have another module here which is called an Explorer, which allows you to find the sensors. You need to be able to find the address of them so you can actually get to them first, but we've got a solution to that. But yeah, I believe it's the first public surveillance network out there. And we've then built this, which is 4D Sky. So 4D Sky is our flight tracking application. This shows you what a successful integration with a neural network could look like. This is just a 3D UI, basically, and it provides you see those little lines on there, they're basically showing which sensors are tracking which aircraft. But we've got 5 or 6 sensors seeing aircraft down there in the southwest of the UK at the moment, out to the Isles of Scilly. But we're getting pretty much near real time on that. Latencies of around about 10 milliseconds, which is significantly lower than what you would get through a general cloud-based network. You can do some other clever stuff with it, which I'll show you a demo of in a moment. This also has APIs. So if you want to be able to host this and provide API and sell API access to people, you can do so. And it's open source. Just list out the real. Where are we?
So what are the different integration options for that 4D Sky you've just seen? Well, you've got the web browser. You can go to 4dsky.com. You can watch planes flying around. But that's generally hobbyists who would want to do that. It's not really that useful. Maybe for a situational awareness, you might want to use it. But as I say, it's free. You can access it, no cost. Create an account, log in, data viewable in the web browser. You've then got the API integration. So if you want to be able to get an API feed from that, you can do. And you get access via the 4D Sky server. But you're obviously reliant on our server then. So if we decide to switch our server off, you stop getting access. The other way you can do it is you can host your own version. So as I say, it's open source. You can run that software yourself on your own server. You're fully in control of it. You can modify it, improve it, change things about it. All you need to do is pay the sensor guys for their data. So if you want to access a bunch of data from different sensors, you just pay them for it, and then they'll give you access. Or you can go for a full SDK integration. So if you've got your own software, say you've got UTM or something, you want to integrate it, you can get that sensor data directly from those sensors into your UTM. And that can be useful because you don't want to trust us. You don't want to trust our Fusion engine. Like, how good is our Fusion engine? If you want to take that to the CAA and you want to go and get that assured, how are you going to do that? You have to ask us for our code. If you've got the raw data packets from the sensors, then you can go through the full assurance process that's fully in your hands. You don't even need to talk to us. And the reason I've put that graph up there as well, there's two factors really there. It's level of customization and the level of independence. So how much of it is under our control, how much of it is under your control, and then how much of it can you change and how much of it can't you change. You could argue they're kind of similar things, but ultimately, if you get down to the SDK integrations, then it's basically fully in your control. So now I'm going to show you what that looks like in reality in terms of setting up two servers. So up the top left, we've got 4D Sky. So that's the live one hosted on 4dsky.com. So that's just on the Google Cloud server. You can see we've got sensors all over Europe. That's actually growing at a crazy rate at the moment. I think we've got now we've got 3 continents, sensors on 3 continents now. This is a local version, you see there. The blank one is a local version hosted on, well, Nick's laptop at that stage. And here we've got the Explorer. The Explorer is just basically a program, again, open source. You can run one yourself if you want to. But what it does is it shows you where all of the sensors are. So you can see some of these sensors here. We've got others going up very shortly. If I click on one sensor, I can see that there's one sensor currently connected, which is, for that purpose, there was a number associated with it, which if you go there, you'll see it. It was actually that one there, yeah, which was 3196. So that 3196, you can see there, is actually connected to all of, that's the 4D Sky you're seeing on the map there. And that's connected to all of the sensors on that map. So you can see both the apps and you can see the sensors. We'll improve that over time. This is kind of a bit of this bit works, but it's probably needs some UI improvements over time. But you can see that's the 4D Sky. You can see at the top, app.4dsky.com. That's running live on GCP. And the blank one there on the bottom left, you'll see is running on a local machine. But we're going to turn that one on. We're going to connect that to a single sensor. We're going to connect it to St. Mary's Airport, for example. So Nick's doing a little bit of fancy stuff in the background. He's going to basically start up the SDK and get the SDK. So basically, it's running essentially a node. So that on his local machine. So his node is essentially now going to connect to that sensor. But what he needs to do is then go to the Explorer and say, hey, can you tell me how to connect to this sensor at St. Mary's Airport? So he needs to run that bit of code, which he'll do in a moment. And basically, that will allow him to do some very secure IP swapping. So we can communicate between ourselves without making ourselves vulnerable to outside security threats. So he's going to start that up. And probably before he's even zoomed out to the 4 screens, that should hopefully be up and running. There you go. So that's now a second app connected to the same sensor. So 4D Sky up the top right, a local version running on his local machine up the top left. The one on the top left is only connected to one sensor at this stage, just to show some differences. Otherwise, you might just say we're screen mirroring.
And if we go to that sensor now on the live Explorer, explorer.neuron.world, and you can actually view this, you'll be able to see now that there's 2 connections to that single sensor. And ultimately, that's what we're doing. And you can have really as many connections as the bandwidth will allow you. That can be set by the sensor operator, but we've had no problem with lots and lots of connections up to now. And there's actually ways of scaling that to an infinite number of, well, maybe not an infinite, but certainly more than you need number of connections. And that is the demo of 4D Sky and the Neuron connections. Let me just move to the next one. Bear with me a second. So how do we deploy sensors? So we've got 2 models for deploying sensors. We've got public deployments, i.e. anyone can buy a sensor and plug it in to the network. Or we've got targeted deployments. Public deployments, when a user purchases a sensor, they sell their data to other people. We sold 70 sensors in the first 3 hours. We had to shut the window because people went a bit crazy. So we end up with having to put 30 people onto a waiting list to buy these sensors. We've got targeted deployments, which we've been doing on our own projects. So we've got obviously Cranfield. We've also got a project down in the southwest in Cornwall, where we deploy them ourselves. We want them in specific areas. And so we can use the public sensors that are already out there. But if we need the one in a particular area, we can say, well, we need an additional one there. We need an additional one there. And we can do that. We can use 4D Sky for modeling. We've got a modeling function to do that, which will model in 3D where the sensors can see. And then get the sensor status from the Explorer. So once we've deployed them, we can actually track whether they're online or offline using the Explorer. And the process is you register your account, you set up your device, whichever device that is. In this case, it's a Jet Vision Air Squitter. You can check the status on the Explorer, and then you can integrate that into the 4D Sky and track your flights. So it's quite a simple process. And I talked about the modeling here. So we've done a lot of modeling for Cranfield. You can see that circle, albeit it's not very pretty, but that's Cranfield ATZ. And what we wanted to do is to work out whether we can meet the 90% detection rate as per JARIS Annex D for Cranfield for the operational volume. And we managed to hit 97.9%. The 2.1% is pretty much at ground level. So obviously there is a limit to how low you can see. But we essentially, you'll see on the right-hand side, you can see why that is. So there are areas where you can see right the way down to sort of 50 to 100 feet, even down to ground level in a lot of areas. But once you start getting to certain areas, depending on the undulation of the land and things, you might go up to 200, 250 feet. But that's generally adequate for most operations. And then the software assurance piece, we mustn't forget that, because that is difficult, very difficult actually. It requires a lot of time and effort, but you need to know if you're building the right system and are you building the system right. And we have been following ED 109A to AL assurance level 4, albeit we're not done yet. There's a lot of work involved in assuring systems, but we do believe that a lot of users of Neuron will end up assuring their own systems, but it's probably not a bad idea for us to go through this process with our own as well. And so we have been generating automatic testing, so unit testing, integration testing. We've got a test report that, and basically a calendar which allows us to show when all the tests were completed on what different version numbers and stuff. But we've still got a lot of work left to do on that to go and get that qualified. But we've seen the recent CAA, DAA notice and talks about DALD, so I'm hoping that maybe some of this is also applicable. And that's that. So Southampton, do you want to do the ground risk? Thanks.
So hi, I'm Bob Masul. I'm from the University of Southampton and work in Southern UAV. And in this project, we've acted as an operator, but also on the ground risk side of the project. So who is Southern UAV? What do we do? We mostly work alongside our university side of things, so teaching, work on designing, testing bespoke UAVs and doing it to fulfill bespoke research missions and research questions. Through this, we have, and through many years of building bespoke UAVs, and you can see a few of them on the screen there, we've realised that reliability and redundancy is something key to build into the system. And this helps build into the safety cases that you need to place for flying these in BVLOS or in the specific category. The top left drone you can see there is called Spotter. That is our workhorse research platform, and that one requires a operating safety case as it sits in the it's a 35 kilo maximum takeoff weight aircraft with a 4-meter wingspan. And so because that sits in the specific case, we have an operating safety case to go alongside that. As an operator within Blueprint, we are the end users of what you've seen presented so far. So the implemented UTM systems taking the service data or the surveillance data and taking it through to the UTM systems. We're also a provider of an operating safety case. And for those who don't know, it falls into 3 categories or 3 volumes of that safety case, which is volume 1, the operations manual. And to build this operating safety case for the Blueprint side of things, we've had to focus a lot on those BVLOS operations, how we can integrate it into a TRA, and how we build up the flight volume, contingency volume, emergency buffers, and adjacent airspace. We've also had to increase our description of UAS systems, such as known failure modes, and to improve and provide evidence for how we're going to operate in the TRA. And finally, volume 3, the safety risk assessment, which we base as on the bow tie model. All those changes that are made in volume 1 and volume 2 feed into that and give us a risk assessment to the operations. And it's worth now considering those 2 categories of being an end user and the operating safety case and how they sit in terms of risk. And from our point of view as an operator and the end user, all the UTM side of things is based on air risk, whereas the operating safety case has to consider both the air risk and the ground risk. So where you're flying, what you're flying over, and what the likelihood of this aircraft coming down over a populated area. So keeping that in mind and moving on to the ground risk side of the talk here, at the University of Southampton, we've produced a ground risk model, which is based on those 4 categories you can see there. So population density, time of day, altitude or other operation parameters, aircraft parameters, and weather. And this was completed by Alexei Pilko. And if you're interested in the publication for it, there's a link there in the DOI just to follow that. If we look at the top 2, the population density and time of day, the model works on a macro level. And it looks at the census data, it looks at the land use data, and it looks at the NHAPS, the National Human Activity, I can't remember the P for it, system, but it looks at the movement of people and how the population density shifts over time in the kind of different land uses, so from residential to commercial and so forth. And on the diagrams there, or the maps there, you can see varying population densities from 1 a.m. all the way through to 5 p.m. and how they move around residential areas and business and industrial areas. If we then look at the final 3, so looking at the altitude, and we can get an idea of the kind of ballistic trajectory of an aircraft that was then falling out of the sky on the ground risk. We can also look at the failure modes and the failure rates of the aircraft. And we can also look at the weather and how that influences the flight plan and the ground risk of that. When we then look at it as a big picture, the ground risk model produces a macro level ground risk map. And you can produce that as a kind of heat map or a map you can see at the top there. And that is ideal for doing route planning and A to B missions where you're covering a large distance. And with that and the weather data, you're able to then plot the lowest risk route from A to B. In terms of doing it on a micro level, though, which is then necessary on most of the drone operations you operate on, you have to then fall back to the ConOps, the concept of operations, and the operating safety case. And this involves looking at the settled areas, the road traffic, and implementing some strategic and also tactical mitigations. And to give you a sense of what that involves for a Cranfield trial, And this just gives you a sense of kind of the detail that the CEA need to see in an operating safety case. Looking at a map of the airport, we can start to plot all the populated and settled areas, including residential, industrial, commercial, and so forth, areas that are classed as people containing uninvolved persons. We would then put an emergency buffer of 150 metres around that, and this is all done some in-house code. You can start to see the bottleneck that Cranfield Airport actually produces to do operations where you can't go into that emergency buffer. Following on from that, then you can create a contingency volume, which is the area that you want to be able to fly in terms of if you need to make any avoidance manoeuvres, and you can start populating that based on your range, your availability to get comms to a certain distance, or just a restricted area that you need to be flying or operating or surveying. And then finally, within that, you can produce the flight volume, which is the area that you actually want to do your mission in, and then you can use that to then start studying other things on the ground, such as road networks and road traffic, and looking at population on the road to get an idea of traffic flow through there. The green area on there is then fed into our ground control system, and we can then use that to make sure we are conforming to our operational intent volume. And that then, I believe, leads me on to the next slide, which is to hand over to DA, who is our GCS provider.
So my name is Joe Roberts. I work for Distributed Avionics as one of the tech founders. And what we produce, as Bob's indicated, is drone solutions for aircraft from 4-metre wingspan right through to the Wind Racer's Ultra aircraft at 10-metre wingspan, 450 kilo MTOW, primarily focusing the fixed wing space. As I was mentioning there, we do full hardware and software stack, and we're very proud of our UK supply chain for the avionics manufacturing. This has helped, and the image in the background you'll see here is Wind Racers flying out of St Mary's Airport in the Scilly Isles. This has helped them achieve some of the only BVLOS permissions in the UK for commercial services. That will start next week in the Orkneys. We've built this system on a patented no single point of failure architecture, which is a step change in the design of traditional avionics products. It's not a focus of this project here, but it's a key part of the safety argument that all of these projects rely on. And fundamentally, all of this leads us to do the BVLOS operations as just mentioned. So where are we right now, and where will Blueprint help us get to? So right now, we have arguments for BVLOS safety in an apron-to-apron autonomy. So that's the aircraft's on the runway, you press a button, it takes off, completes the automatic flight and an automatic landing. Obviously, at any point, the human can intervene in that process, but we're at the stage now where that is becoming a normality and a routine part of our operations. These operations currently happen in controlled airspace. Now, whether that's a TDA or an existing danger area, we're still limited and bound by the controlled airspace practicalities. However, throughout all of these processes, we're continuously gathering evidence, both with the wider GA community and commercial stakeholders, that this type of operation isn't obstructive. It can become part of the airspace picture. And a couple of the images down the bottom there show operations we've done where it's greatly benefited the communities. Bottom left one, he won't like flying in fog in the Orkneys. And on the right-hand side, we're servicing Fair Isle of 60 people, one of the most expensive routes that Royal Mail have to operate. So where does Distributed Avionics fit into the wider picture? And Bob's shown you a little bit here of how our software can support their operations. You'll see a bit more of that in the demo. But really, we come in between the human and between the UAV. And how does that then fit in the picture of Blueprint? So we're talking about ADS-B primarily here, but you could see this as any type of input, and we're doing a lot of work with digital radars coming up in the either extension of this project or in future, but ADS-B only here. Either the ADS-B comes in via the UTM service or through the ADS-B network direct with Neuron, or the aircraft itself carries an ADS-B receiver. So there's two methods of input for ADS-B information into our system. The latter one is very important. So if the network or system isn't able to sustain coverage in that region, the aircraft itself can report the ADS-B back and perform the detection of the aircraft in those regions. So what does an aircraft detection look like to the human? So again, you'll see some of this in the demo, but just to give you a bit of an idea of what the UI looks like. On the leftmost side here, we're in what we call a nominal condition, where there's no indicated threats to the current mission and the current trajectories of obstacles in the region. So you see there just below the 4 in the center of the screen, there's 2 aircraft indicated. These 2 are not on a collision course with the aircraft and therefore don't present an issue to the user. And obviously this picture evolves over time. And in the center there, we're seeing a caution, so we're getting a warning to the operator that there is a potential for a collision in the future. And then the rightmost one, the collision's now been cleared. The aircraft, in fact, continue to bank right, and then we go back to a nominal state. One of the key things about Blueprint, as James has alluded to, is that this isn't a monopolized service. This isn't going to be something that's locked into one provider. And we actually already use Planefinder as our second source of data input. And we can see this very much as multiple sources of data will come into us as we grow this product out. Some of it will be Neuron, some will be Planefinder, some of it may even be companies that don't exist yet. But crucially here, we can integrate with multiple traffic sources. I'll talk a little bit now about how the detection and tracking system works, because this is quite a core part of why a safety argument can be made. Now, the rightmost side is a bit of a flow diagram, which I'll quickly whip through as a bit to digest. As I said earlier, the obstacle data can come in from two places, either detected from the onboard systems, chiefly like a PingRx or some other ADSB end product, or it could be rebroadcast from the ground networks. Then what we do is we rebroadcast the data from the ground up to the aircraft. The aircraft holds a continuous model of all of the other obstacles in the region and is doing a 100 Hertz obstacle modeling of whether or not there will be a collision in future. Why that's very important is trying to avoid a fighter jet is very different to trying to avoid a multi-rotor, and it's important that we look at the temporal actions of the obstacles that we're trying to avoid. Once we've worked out the time and distance to closest approach, we then classify the threats, and we will act on the most serious threat at any one time. And as you can see on the bottom left here, the aircraft's very clearly at that point in time on a collision course, and we are not aware of what other obstacles may be taking in terms of their path, so we have to assume the worst. Once the threat classification has been done, either an avoidance action is taken, or the data is broadcast to the operator, and the operator can perform that avoidance. The avoidance action is really only happening as a very much last resort, similar to a TCAS-style system, but in 99% of cases, we'd expect the operator to perform the avoidance themselves. So where are we in the project? So this was a slide I presented back last year, and at that stage, we just achieved level 1. We've now successfully achieved level 2, and you'll see a bit of that in the demonstration today. Level 3 is still to come. So the fact the action is carried out automatically, great, we've demoed it. That's not yet been approved as a formal safety method for BVLOS operations. And we're working through that at the moment, and we'll continue to work on that through the Blueprint project. And one of the key things of all of this is we'd like to implement a smart mission-based predictive path. So at the moment, the aircraft that you're, either yourself or the aircraft that you're trying to avoid, you're not necessarily cognizant about what mission they may perform. If we have that knowledge and we have better shared information around missions and expected path, we can then much better optimize the collision avoidance system and ultimately get a denser airspace picture. Thank you.
Hello, everyone. Thanks for coming today for today's event. My name is Carl Schilip. I'm the founder and CEO of Skydrones Technologies. We are a London-based company who designs and manufactures avionics. This is the hardware and software for drones, including the ground control station software. And for the last few years, we also started our UAV manufacturing and operations business. So we create the VTOLs just like this one on the picture. This is 2.5 meters wingspan, and we have the whole range of the aircrafts from 2.5 meters to 4.8 meters, including the one which is 3.2 and 3.5. So these are quite capable aircrafts which can carry up to 7 kilos payload and travel for the range of up to 500 kilometers. So basically, these are various VTOLs we offer. Also, our products can be used on the multicopters and traditional fixed wings, but VTOLs are the most important products at the moment because they can provide you very tight space for takeoff and landing, and at the same time, they can carry quite a lot and travel quite a lot at significant speeds. Also work a lot on the payload integration. So if someone would like to put a camera or some different equipment on board, that's something we can do. And most of the partnerships are coming with the manufacturers of the payload equipment and the companies who use drones for the benefits of just improving their own business with different companies across Europe and the US. One of the key products we offer also is the AirLink. So this is the 3-in-1 flight control system. So this includes the autopilot, the mission computer with AI capabilities, and 5G connectivity. So that's quite compact and control any type of the aircraft, from small ones to large ones, including the manned aircraft. And just one of the latest news is that AirLink passed certification from BT, British Telecom, just last week. And that's the first unit which is approved flight control system with integrated communication capability in the UK. Next slides are going to be about our participation in Project Blueprint. I'm just given the word to my colleague, Yuri Stelmak, who is the project manager for Blueprint in our organization. and he will tell you more about our activities in there. Thank you, Kirill.
So you just saw the Airlink unit as of now here, and it's a core of all our UAVs. And now we have all the technologies like Neuron and Drone Cloud, all the technologies integrated, and we built all our aircraft based on this Airlink unit. So from dissemination perspective, like exploitation of this project, it's quite important to say that it's easy now to implement all those features in all our upcoming aircraft as well. So, yeah. And now I'm going to show you how all this works from operator perspective. Here we will talk about strategic deconfliction. I have a short video on this. So we plan some kind of flight operation. You can see a mission here, and we're going to submit it to Drone Cloud. That's what exactly Andrew demonstrated, but we have a conflict. So we can't fly this mission actually. And now we go to Skydrone's cloud. It's our flight operation environment. It's developed by Skydrone's web application. And now we deconflict the mission. So we altered this mission just in our editor and web application. And now we resubmit this mission. And we can see that now there is no more conflict. So it's deconflicted and we can proceed further. Here, yeah, no conflict detected. So it happens just online in a few minutes. Yeah, thank you so much. So the next screen is also flight operations from operator perspective. We can see, here we can see Skydrone's cloud web application where we plan our missions. Here we can see Drone Cloud system, and here we can see Neuron system. Now we have the mission. The mission is already approved. And now we are going to start this mission. So we press start mission in Drone Cloud system, and after that we launch the mission in our Skydrone's cloud system. And we can see that our aircraft will stream the telemetry via internet to Drone Cloud system and also to Neuron system. So we stream the telemetry to Neuron system via internet and also via ADSB as well. So you can see the aircraft starts its mission, and Neuron system also sees it, and Drone Cloud as well. Also, you can see in commercial traffic in Skydrone's cloud. So it's commercial aircraft, but it flies high, and we have vertical separation. It doesn't affect our mission. But we see all them in our web application in real time. So everything is here, and the pilot has awareness about the situation. That thanks to Neuron sensor system. Let me. Now our aircraft leaves its mission, and now it becomes non-contingent. Here, this is what Andrew showed you. So we have this, and after that, when aircraft will return back, it will become contingent, but Drone Cloud already knows about this and report this incident. So yeah, now the aircraft become contingent, it continues its missions. I'm going to the next slide. Here is just a short demonstration of how Neuron data feed looks in our Skydrone's cloud. So there are plenty of commercial traffic here, and like in every moment, our pilot can observe this traffic, and also we have some deconfliction procedures that you will see a little bit later. So, next one. Yeah. That's a real-world demonstration of, sorry, but I will speak. So, real-world demonstration of how this works. We see the copter, a multi-rotor aircraft that flies its mission. So we see it on the laptop screen. And now you will see this commercial aircraft in the sky as well. So we are on our flight test field. You can see the multi-rotor aircraft just in the air, and like wait for a minute, you will see commercial aircraft also here passing by. So all this happens in real time. Here. And the last but not least piece, we also have our Skydrone's Cloud application. We have the drone flying its mission. So it does some kind of inspection mission. We see the video feed from the drone right here. And now we can see the air traffic. Now one of the aircraft entered our flight operation area and it becomes not safe. So you can see red on the screen. And now our pilot is aware about this situation and will take some preventive measures to avoid this conflict. So I will show you once again. It's quite a short video. So yeah, the aircraft is flying its mission, and you can see plenty of other aircraft that we get from ADSB feed. And now aircraft enters, and the pilot sees it. So it can avoid conflict by landing or doing something else. So that's what we have. This is how it works from operator perspective, and we can scale it so we can deploy it on a lot of other drones that we manufacture. Thank you.
So, very good afternoon. I'm Vijay Shankar Dwivedi, research fellow in guidance, control and estimation, Center for Autonomous and Cyber Physical Systems, working at Cranfield University. We have worked for the deconfliction in the presence of wind field for an environment where there are multiple obstacles like buildings, mountains, or some no-fly zones, and other UAVs moving in different directions at different speeds, which are intruder for the reference UAV. Our deconfliction methodology utilizes the uncertainties in the UAV's relative positions and sensor noises, and the error in the UAV position due to the instantaneous wind gusts. We are determining a dynamic waypoint that ensures safe passage of the UAV with the minimum separation, and also which ensures the minimal control effort for the UAV. Our methodology starts with the estimation of the wind field, which uses a machine learning based approach. It utilizes the aircraft control input history and its trajectory to estimate the wind field, and using this wind field, we are able to find the position error due to the wind gust in the UAV position from its planned position. And based upon that, we are able to estimate the collision probability, which ensure us to find the path which ensures the minimum, a collision-free path with the minimum separation. And utilizing this information, we are finding a waypoint, a dynamic waypoint at a look-ahead distance, which ensures the minimal control effort for the UAV. Here is a small. So the rest of the UAVs are the intruder for the reference UAV, and all are avoiding their the possible collisions and reaching to the destination waypoint. And meanwhile, they are generating the intermediate waypoints to reach their destination. Thank you.
Good afternoon, everyone. So I'm Glenn. I'm from Ebonai. Ebonai is a safety and systems engineering consultancy. So we typically provide first the type operations and safety and mission critical systems. We look at the safety assurance associated with those. I belong to the future air mobility part of the organisation, and that feeds into two units, ATM and Airspace, and the other unit is Aerospace and Defence. We also naturally have a close coordination with other units within the organisation, but typically cyber and digital. So many of you here are familiar with the Specific Operations Risk Assessment, or the SORA. It's an industry recognised tool, and we find it actually quite useful to look at the end-to-end safety requirements. So not just looking at the drone operations, but looking at the drone operations in the context of the airspace and the supporting technology. So looking at the holistic safety assurance for a blueprint environment. So it guides what needs to be tested and validated based on both air and ground risk, and you've heard some talk about that already today. And obviously there's methodology and process behind determining those air and ground risk classifications for a particular blueprint. But it is quite a high-level guide, and it doesn't necessarily tell you what standards are relevant. So we did further research on standards, and we aligned with the EU research and typically the Shepherd report. And we also did further hazard assessment with the help of hazard bow tie modelling, and that was to look at a little bit more detail in terms of the mitigations to reduce risk, going 1 or 2 levels down compared to what SORA would necessarily tell you. And importantly also to use that hazard bow tie modelling to relate test evidence back to operational outcomes, so to feed into operational testing, operational trials, system testing, and also then to bring that back to the requirements to influence them based on the results. So again, just looking at the holistic picture, the end-to-end safety assurance, as I said, we didn't just look at the drone operations, although as you heard from Bob, there is already a operating safety case that is associated with that needs to get an operational authorization as a drone operator. But we used the SORA to look at the wider picture. So for example, with the airspace, to look at the standard operating procedures, to influence emergency procedures and the human-machine interface, but also the various interfaces, the human-machine interface, and the systems themselves. So looking at the technical integrity and reliability and performance of the various systems, UTM, ATM integration, UTM itself, and obviously the strategic and tactical UTM services, and also the detect and avoid network. So this is just a snapshot from the bow tie model that we used. This is the left-hand side of the bow tie model, looking at operational hazard, looking at the causes to the operational hazard. And we initially split those into the capability areas in alignment with CAP 722A, positional awareness, situational awareness, and command and control. And on the left-hand side, you can see, again, just a snapshot of some of the causal factors related to those. But importantly, we wanted to relate the mitigations in purple there from barrier model back to the SORA requirements. We needed to link the more detailed barrier model back to the SORA requirements. And this is just an example of Operational Safety Objective 4, system developed to design standards, and with the help of JARA SORA Annex E for OSOs. Again, this is just a snapshot of requirements and evidence that we've derived with the help of Annex E from the SORA, and also with further research on the standards. And as I said before, we can then use scenarios related to those to influence the test evidence through the operational trials and through the system testing. So we use the hazard bow tie model to do that, which is now linked to the SORA steps. And similarly, on the right-hand side of the bow tie modelling, looking at the operational outcomes from an operational hazard, we related the mitigations to those outcomes, related to those outcomes back to the SORA. In this case, looking at the tactical mitigation performance requirements from the SORA. And again, with the help of Annex D from the JARA SORA, we can understand more about the high-level requirements behind those. And as I said before, we related the standards against that as well, based on some research. And again, this is just a snapshot, isn't the full list. And similar to before, again, we're able to relate those using the hazard bow tie model, relate methods and scenarios to test some of those issues and how they would be mitigated, and to influence system testing in accordance with the standards and guidelines which we researched, and to influence the issues recorded in check sheets, and therefore to bring it back to the operational procedures and obviously the systems as well behind those. So that just gives you just a snapshot, very high level overview of what we did to help influence the regulatory requirements. And I believe before we go to a break, you're going to introduce the next session, James?
Right, okay, so now we get to the bit that is a bit more risky, and we hope it all goes right today. Please bear with, there's a lot of moving parts to this. We're not talking about one operation, we're talking about 3 operations with UTM systems in the loop, ATM systems in the loop. There's a lot going on here today. But what we'll first of all show you is, what does this look like in real life? Like, we've shown you the tech, we've shown you, the regulation, we've shown you the assurance, we've shown you all the pieces, but what does that look like to an operator in real life? So we've got 3 flight plans, the first of which is a VTOL BVLOS UAS. So this would be this is a real drone. You might just see it just over on the road there. It's actually flying visual line of sight in this circumstance, but it's mimicking a visual line of sight operation. It's actually being flown from a laptop. We've just got a safety pilot out there just for extra safety measures. We've got then a fixed wing, which is going to take off from the runway. So that's going to be doing flight 2, which is going to do a circuit basically of the airfield. That's it done in a simulation environment, because what we're going to show to you is actually avoidance. And you can only avoid things in any direction if you're in an emergency scenario. It's actually really hard to enter an emergency scenario in real life, because firstly you have to put things onto a conflicting course, which is hard to do and get the regulator to sign off on. But secondly, it also means you're restricted about where you can fly. And then the third piece is your typical visual line of sight operator. So we don't want to ignore the situation where you've got existing drone users or hobbyists that need to still be able to operate within this ecosystem. If you tell them they're going to have to put a 500-pound ADS-B transponder on their Mavic Mini, which weighs 250 grams, and the device weighs 250 grams, it probably won't take off very well. So we need to be able to accompany the existing airspace users as well. So what we'll show you is Flight Plan 2 being approved by the ANSP, Flight Plan 3 being approved by the ANSP, and then Flight Plan 1 conflicting with that Flight Plan 2 of UAS 2. So we want to show you actually what happens in a live situation. And that's really to validate the UTM strategic conflict detection and the ANSP approvals. The second part is what happens after that. Well, okay, I've had a conflict. What do I do? Well, the pilot will then replan their flight, move it to a different area, and the aim is then to validate, the MVP of how we'll actually go about replanning our flights if there's a conflict. You could move it in time, you could move it in geography. In this case, we can't move time around really very easily, but we can move the geography. So that's what we'll demonstrate today. The third part is what we're going to do, which is basically around conformance monitoring. So the UTM will alert the pilot of a non-conformance. They've got an operational area or operational intent volume that they're flying in. The UTM will alert the pilot of non-conformance when they fly out of it. They'll then set the status to non-conforming, so other UTM providers will also be able to pick that up, and that will show within their UTM system. Other US will obviously be then notified via the UTM. The pilot will re-enter the OIV, and the status will then go to conforming. And the aim is to validate really the UTM conformance monitoring functionality as part of Demo 3. And then finally, the fun one. So we've got a real aircraft. It took off about 30 minutes ago from Cranfield. It's currently circling over, you see that racetrack down to the bottom right of that picture. So he's currently trying to drive around the racing track. He's probably dizzy by now, but I'm sure hopefully he'll be flying in a straight line for this demonstration. But the intruder will enter essentially the TMZ area. We don't have a TMZ in place, obviously, but they will be entering and flying over the ATZ. They'll actually be at 3,000 feet. We don't actually want to put these things on a collision course in real life. That would be a bit stupid to do. But we'll have all of the other UAS flying below that, so there will be vertical separation. But they will come into conflict in a 2D sense. So we want to test these alerting systems for their functionality in a two-dimensional sense. What we've done is we've set the alerting system to trigger up to about 4,000 feet. So you could reduce that to, plus or minus 250 feet. But for this, we've set it to 4,000 feet. So it forces it to alert the other operators. So we will put them on a conflict, but they will be vertically separated. So that'll hopefully keep the CAA guys happy. So let's swap cables and let's show you some
some demos. So, okay, we're good. Right, so what you see here up the top left is the 4D sky view. So you'll see some stuff going on. You'll see just to the left of the airfield, you'll see sky drones sitting there. That's a real aircraft, ADS-B equipped, a real drone sitting on the runway. You'll then see, sorry, not on the runway, just off on the campus, just over there actually. That's a real aircraft, real drone. You then see another drone sitting on the runway. That's not a real drone. That's a simulated one. And then if you go towards the bottom right, I don't know if you can see that around the racing track, you'll hopefully see, he's just done a figure of 8, he probably got a bit dizzy, but he's going to head back down to that racing track down towards the south, and he's going to, should be holding in that location. So that's that one, yeah, just to the bottom right of your mouse there, Nick, if you can hear me. What is it? Oh, Spotter. No, Spotter is the other one. In the other view, on the top right, if we just go and move it to the other view, you will see DA's distributed avionics view. So that's that one. You've then got down the bottom left, down the bottom left, we've got the ANRA CTR, which is what you would see from the airport's perspective. And then the bottom right, you've got the GCS for the aircraft, which is just over there. So they're the 4 screens we've got today. We'll also see the flight planning. So maybe if University of Southampton, you could load your flight and import it into Drone Cloud. So what you're seeing here is so this is University of Southampton are just loaded their mission from their GCS. They've imported it into Drone Cloud. They're setting up the parameters for the conflict, and they are now about to go and put that into the UTM. So that's now broadcasting into Open UTM from ANRA. Now other UTMs can now see that. That's the key, really, is you've got the interoperability happening there. You've then got that now appearing. If you see on the bottom right screen, you'll see that their flight plan's now appeared, so you can actually see that other flight that's in place. Now, if the other UTM, if Sky Drones could now import their flight plan, yeah, that's the one. So you can see we've got a conflicting flight plan here. So literally doing it live at the back right now, as you can see. So if it's a little bit glitchy, this is why. But you can see conflict detected. Okay, they've literally just done this live. Conflict has been detected in that region. They're not allowed to fly there. Okay, so now they need to do some kind of replanning. So they're going to set up a second flight plan that isn't conflicting. And we'll show what that looks like from here. So there we go, they're copying that across. Setting the times, setting the buffers. I can't read what that says, but they're doing something else. And I believe that's now been approved. Has that been sent for authorization yet? Okay, now if we could move to the ANRA screen. So what we want to show from an ANRA perspective is you can now see that the flight is now come in there. So this is the flight. You can see where they're ready for approval. So now the airport will have an option to then decide whether to approve it, reject it, or amend it, I believe. So they then go through that process. They can approve it. And remember, all of the UTMs, all the drone stuff is deconflicted before it hits the airport. That's the key, really. You don't want to be given an airport stuff that hasn't already been deconflicted from other flights. So it saves workload on the airports. And now that flight plan, I believe, is now in. So am I right? We've got both flight plans approved? Is that good? Yeah. Okay, great. So we've now got both flight plans approved. So I guess we move to the next phase, which will be to actually do some flying. What we'll need to do is the should we kick off as well? Yeah. So what we should now see is University of Southampton will be taking off from the runway. So if you could just do a zoom here, zoom in here. There we go. So University of Southampton are now taking off. Again, this is a simulation. So okay, and now Skydrones should be just requesting authorization to fly themselves. So we should see, hopefully, in the next few minutes, them take off as well. So you'll see at the moment that they should be preparing for takeoff. You can see their FPV view there at the top right. This might take a couple of minutes because this is happening in real time. And if you peer over through that window, you'll probably see it take off. There we go. Okay, propellers have started. Okay, so they're now taking off, and they're going to follow their flight plan. Okay. So what you'll see is they actually already had an object detected because the other drone was already close by when they took off. But now they're going to start their flight, so go through those waypoints. And at some point, you can see they're doing an example road survey. So flying over the road, capturing photogrammetry data to model it. It would be done on someone like Highways England. This would be their bread and butter, doing topographical surveys. And then at some point, they will then go into a non-conforming status. So they will move the aircraft out of the area and basically move to a non-conforming status. So if you could just zoom out. And hopefully you'll also be able to show when they do go into non-conforming status. Maybe if Volga could show us the drone cloud screen so that we can view it when it goes non-conforming. Okay, is it now flying outside? Am I seeing it correctly? Yes. Bottom right screen.
James?
Yep.
Sorry, you started way too early. There's a 5 to 10 minutes wait before we can start a mission. You've planned the mission, you had to wait. You couldn't start immediately.
I'm sorry.
Yeah, so you're unable to start the mission on drone right now because there's an actual time delay.
Okay.
Including by the DSS and all of that. So
Okay.
yeah, it had to be a wait there.
Oh, sorry. I've gone to.
Minutes, I think it's 25 past. They said their mission for.
Yeah, is your start time 25 minutes?
25 past 3 would be the start time. So.
Okay. No, sorry.
Until then, we won't be able to do anything.
Yeah, understood. Sorry about that. Okay, I've had a little bit of a mess up then, but basically the conformance monitoring, I think what you saw earlier is how it works. So when it goes outside of the OIV, what it will show you is a non-conforming status, and that will do that. So if we could now move across, where are we? Yeah, so now that would be outside of the operating volume there. So if you could just switch to the other screen, go to the full screen, that's fine. Okay, so we've got Drone Cloud operational, we've got DA now circling. If you could just move to the DA screen. So we've got DA loitering at a point just sort of southeast of the runway, so at point 3. So that's them. If you go down sort of just a little bit towards the south right, there you go. So that's the intruder aircraft. That's a real aircraft we've got flying, and we're going to put them on a collision course soon with a radio call. And if you could just switch to the Skydrones screen. Okay, so we've now got Skydrones following the waypoint flight. Okay, so that's now flying, and if you could zoom out a little bit, just so we can see the other aircraft. Should be south. There we go. Okay, so now if we could just go back to the 4 screens again. And can we pin maybe both of those screens, so pin DA and SkyDrones to the screen. I'm not sure we can pin to the screen at the same time, but that's okay. Oh, there you go. Okay, so we've now got SkyDrones and SkyDrones and distributed avionics. So this is their ground control stations that are now live and operational. So do you want to start the conflict? So Bob's now just going to speak to the pilot, or get hold of the pilot through via ATC. He's going to put in a call into the pilot to send them over the runway. So their instructions are to basically fly over the southern end of the runway, which should put them onto a conflict with both distributed avionics and with SkyDrones pilots. So if you just have a look, can we see them both? There we go. So on the left-hand screen, you'll see the crewed aircraft, and you'll see both the drone circling at just between 0.2 and 0.4 and 0.3, and then you'll also see the SkyDrones UAV also showing up on their screen, just sort of up and left of the red arrow. So there you go. You can see the two aircraft. There's actually another aircraft, a real aircraft, which is currently parked up at the airfield pointing north. You'll see on that screen. But hopefully shortly we'll start seeing the other aircraft coming in. So you can see that now on the right-hand screen as well. You can see that there's another aircraft coming in. And at some point over the next sort of 30 seconds or so, you should see the traffic alerting systems functioning on both of those aircraft. So when a drone pilot's flying these missions, what you'll see is that they should always be looking out for other aircraft. But here we go. So on the left-hand screen, you've just now seen a traffic alerting come up. So now what the pilot has to do is decide what to do about it. So they're now going to decide on a avoiding action. And on this occasion, they're going to try and avoid the aircraft by flying away from it. So they've now diverted off that waypoint path and they're now travelling sort of due west. Now you'll see the other drone is a bit further away because it's not on the same side of the airfield, so that traffic alerting system hasn't yet kicked in. But that's a real aircraft now coming over the airfield. You'll see it coming over hopefully in about another couple of minutes. It should almost fly directly overhead us. But that's now, there you go, it's now moving to out the way. And you're just seeing the SkyDrones aircraft now. The drone pilot's now got the alert and they should be now instructing the drone to come in and land. So that alerting system has now popped up. Oops. Just reloaded this screen. But now it should be coming into land, and hopefully you'll see now the drone literally coming into land on the FPV screen. And so it's now just touched the ground and it's now come off over the southern end of the runway. And now hopefully if we look out the windows, we'll see the aircraft coming over our heads. And that is pretty much, I think, the end of the demonstration. But if you want to go and look out the window, you're welcome to. Yeah, thanks everyone. Thanks very much. Should we just move?
Recording stop.
Okay. Okay, we've got one small thing to do, or one small thing left. If this is going to work. I'm not sure which button I'm going to press. There you go. So I guess the next question is, what is next? We've shown stuff working. I messed up a little bit with my timing, so apologies for that. I'll hold my hand up there. I was meant to wait for a signal and I went a bit too quickly, so we didn't see the conformance monitoring because essentially that was, I'd started the mission too early for the conformance monitoring to kick in. But, why is this not working? Let's try again. Is it coming up? So the question is, what's next? Here we go. We do have something. So really, let's just recap what we've done over the last sort of 24 months. So there's a team of 9 companies trying to basically make the impossible possible. With BV loss, we've talked about it for 15 years, pretty much. We need to turn it into action. We need to go and move this over the line now. We've built MVPs. We've integrated them together. We've shown how they can interoperate. We've built a sensor network. We've installed it. We've modeled it. We've seen how that can be integrated into all of these different systems. We've done some initial testing. I'm not saying that's complete yet. We've still got some more to do. But we've done some initial testing. We've shown how this can work. We've seen where the big problems are. We now need to sort out those tiny problems and prove that it works to a certain degree. We've got an OSC approved for TRA operations, and the TRA application is in process. We've got some meetings, I believe, in 2 days around those. So, that is moving forwards. The first one always takes longer. I remember the first swarming operation that was in the UK, drone light show operation, took over 12 months to get the OSC through. Other people are now taking 3 to 6 months to go and get it through. So the process does get quicker over time. The first ones always take a lot of time, but they will improve. But I do believe that what we've done is, at the very least, built a vision or a blueprint for beyond line of sight operations. I'm not sure where that's coming from. But what's going to go on in the next phase? Okay, so, well, unfortunately, we're now down to, we're going to say goodbye to a few of our friends. So we're now focusing really on the detect and avoid element. So there's going to be a huge detect and avoid element here. Future flight money is not an endless pot of money, unfortunately. I wish it was, but it's been very, very generous. We've got a small amount of money now between the 3 companies to help us to do this next phase of work. And really what we're going to be focusing on is the DAA systems. So testing what you just saw there right at the very end, getting that assured and getting that robust, getting that to a point where it can be used operationally, not just at Cranfield DARTeC Center. So we need to validate the sensor coverage using ADS-B equipped UAS. We need to find all the weaknesses in where the coverage isn't good and where it is good. We need to conduct a bunch of simulations to test the pilot decision-making performance. Like there today, you saw them making certain decisions. You saw a UI, user interface, but they now need to decide, well, what do we actually do? If it's coming straight at me head-on, I do this. If it's coming from behind me, I do that. If I'm a VTOL, what should I do compared to a fixed wing? VTOL can land vertically, a fixed wing can't, unless it's one like sky drones. So there's all of these different things around avoidance. So we need to test the pilot and actually have a pilot in the seat deciding how they're going to deconflict. We need to test to validate the command performance. So when I click here, how long does it take me to actually turn to that location? We need to do simulations to assess the execution success rates. So given that I detect it at this distance and I decide to do this action, has it actually avoided by the ASTM requirements, which is spelled out for us now? We need to test to validate the feedback loop. So when I take an action, how long it takes me to go and get an update of the next position. And we need tests to validate the full system integrity. How reliable is this detect and avoid system? How reliable is each component in this? The sensors, the surveillance data processing, the tracking, the monitoring, the alerting systems. And ultimately, that will allow us to calculate the risk ratios, which are defined in ASTM. We've got a list of things that we need to comply with now. We now need to tick them off. And that's quite a lot to do in 9 months. So we hope to get as much, if not all of it, done. So it's going to be carrying on. So it'll be Neuron, Distributed Avionics, and University of Southampton who will continue on this work. We'll try and get through as much of that as possible. But
ultimately, I think we now have a pathway through and a sort of light at the end of the tunnel to say, look, CAA have said if we do this, we should get approval. We do that, and then we can argue with them a little bit. So what does that look like? So in terms of a timeline, we developed the prototype. We applied for the TRA sandbox. We now developed the MVP. We've now got the OSC approved. So the next step is the TRA approval. So we need to go through the TRA. What that requires us to do is to basically do a CAP 1616 document. That's already in process. It shouldn't take as long as a normal sort of airspace change. TRAs are meant to be lightweight, meant to be easy to do. So we do this, and then we do the testing and assurance. So we need to do that in line with the DAA's new policy concept. That's what we're going to be using as a basis. It's largely off existing standards such as JARIS, SORA, and ASTM, but we need to go through that and do it as quickly as we can, really. And that's what's going to take us up to March of 2025. Hopefully we'll be able to welcome you all back here in March and show it all done. I'm not going to promise it yet, but we will do something towards the end of this project and certainly disseminate the activities on what we've done. But yeah, thanks everyone. I think that's it. Thanks everyone for your time. And I guess we'll now accept some questions. So shall we just bring each member of the team up to the front to do some Q&A?
You're looking at detecting void, and that's the next step, and we know that CAA started to work on that. How far through the discussion are you with the CAA as to what standards they'll accept? Because it's been one of the missing pieces in jigsaw.
Sure, I can probably handle that. So we've been part of their TRA sandbox since around about the same time last year, around June 2023. We've also been part of other work with them prior to that. So this has been a long-term relationship with them for at least the last 2 years, maybe probably further than that back as well. They recently brought out their new detect and avoid draft policy concept, which is now out. That's obviously not published yet publicly, but I would say it's probably quite close to being what will be the eventual policy in the future. There's probably some areas of it which might change over the next few months or so, but yeah, we've been very close to them as part of the sandbox. We've been following their strategy, and I would say we're well sort of in tune with what they're up to. I don't know if you want to talk a little bit about the safety case work you've done.
I can do. Is there anything particular you're after in terms of the alignment to the safety case?
Well, I've seen a lot of applications that go in, and people will try and mirror a standard that exists during overseas, for example. And the CAA will say, we don't recognise this, we don't know what we currently accept. So what I'm trying to find out is how far down that route we are, and the CAA will agree with what those are.
So I think what James said about using the draft policy is something that's going to feed into following the standards, and then from our point of view as an operator, we're relying on the GCS provider to also implement some of those standards for the detection algorithm, and those will be following some set of standards that will help promote that.
Yeah, I think just to add to that as well, the CAA are quite clear ASTM standards for DAA. And there's also some stuff in SORA, JARIS SORA, that they want us to follow as well. So the detect and avoid policy really spells out what specific standards they want to meet. They've talked about design assurance level D, DALV, for the integrity level. So that's another area that obviously is quite tricky. So yeah, I think the CAA have now specified some of the things that they want. But they have stated that these are suggested ways of complying, but you're free to use whatever method you wish, as long as you can sufficiently answer their questions. Is that okay, or did you have a follow-up question?
I suppose the question for CAA next is what are those standards?
Yeah, definitely. Anyone here from the CAA? We got you.
Thanks. I'm Barry from the CAA, the detect and avoid link sort of Yes, absolutely. We'll work through that and we'll have the right people ready to work through the details. That's great. I did have a different question though, which was, do any of the consortium participate in the technical standards bodies? And if so, what do you get out of it? If not, why not? Like Eurokai or...
Do you want to take that one, Jeff?
Yeah, so we're starting to participate a little bit in very specific targeted areas that we feel is of direct benefit in the short term for us. So, excuse me, 2019 was quite an epoch for us in terms of hardware standards. I think we're probably all aware why that was the case. And then 2020, with the publication of the AIB report, very quickly shifted our focus onto hardware as a primary means of failure for UAVs. As a result of that, our company very specifically is now involved in a lot of the electronics manufacturing standards training as a result of that. What we're not yet seeing is the exact avenues and streams needed to address that in a commercial sense for things like EuroK and USTM and ATM standards. So I don't want to say it's going to be written in blood, because unfortunately that's what happened last time. But there may be a case here that until it becomes a commercially viable or a commercial block entirely for us, then engagement that's going to be tricky. What I will say is the next couple of weeks for us up in Scotland will be a big telltale of how this is all going to go. So we're flying with wind races up in the Orkneys. Obviously that project happened 2 years ago as well and was ultimately stopped as a result of airspace issues and regulation up in that space. So we're hoping for the next 3 months there'll be a lot of engagement with the stakeholders up there, and as a result of that I expect we'll see a bit more of the targeted standard committees and where we're going to join. We did engage in the BSI process as well through Future Flight, which I think the report of that's been very useful and is helping to pull together a lot of the standards that could be done. But as a company ourselves, engagement with very specific standards bodies only ever really comes as a result of a specific request or a specific area of knowledge. And for us to date, that's very much been in the hardware and manufacturing space, and at the moment, less so in the airspace space.
Next question.
Hi, Lewis from Midlands Aerospace Alliance. So what thoughts do you have next for integrating the system with autonomous systems? I'm assuming that's on your mind.
You're doing some stuff on that.
Yeah, so what we have at the moment is very much an automatic system. Right? So it's a system that you tell it to do a thing and it will do the thing, and it's very tightly defined that that is the thing it will do. What we don't want at the moment is something that may do an absolute array of different options based on a given set of inputs. So we're very much in the determinism space right now, and all the stuff we presented today, very deterministic, very predictable, very reliable. What we're looking to do, and we just started the partnership in the US sadly, because it doesn't exist in the UK, but in the US we're looking to apply AI at the next level above that. So rather than taking determinism out of the air system, we are going to apply the AI at the cloud level, at the ground level, where these things can be done in slow time without affecting the ultimate safety of the operation. So automatic versus autonomous, interesting argument I think we had actually this time last year as well. But we see this as a highly deterministic air systems with then intelligence and AI built around that safe core. So fundamentally, the human at any given point can always override and always step in, but there will be a time where getting airspace density, getting missions planned will eventually be done using AI-enhanced systems.
Yeah, maybe I can also. So as a human function, we have, as we presented, AI-link, AI-capable flight controller, and we are now deploying aircraft for our customers, and they now deploy their own proprietary AI-based software for autonomy. And of course, in most cases, they don't tell us how they use it, but we see a lot of traction on this direction, at least in aircraft autonomy, so in the edge autonomy, in the edge AI deployment. So we see more and more requests, and now we also do some training stuff, and probably we will see in some coming months. So stay tuned.
Anyone else for a question? Neil, just at the front.
Can you hear us?
Yes.
Thank you. Andrew Stevenson, company's FTI Communication Systems, are involved in safety critical networks for airports, control towers, comms, navigating surveillance. You mentioned in response to
a question on standards and bodies there. The AAIB report was focusing on hardware as being a critical area for drones, for UAVs. Cosmic radiation, how much have you looked at that there as a concern? And what do you know about it?
Sure.
Thank you.
Yeah, good question. So this is an area that does link to the same hardware piece. So question on cosmic radiation. During the qualification of the systems for the specific category UAV of wind racers, an EMC process is considered through the product. And what we've typically found with the hardware is we generally meet quite a lot of the aerospace standards anyway, and applying that as part of the development process makes a lot of sense. So DA 160G is a big part of our qualification now for air systems at the avionics level, and we feel that we address the majority of the concerns through the EMC and EMI interactions. Coming on to sort of GNSS and third-party systems, the reality for us is the platform we produce is multi-sensor. So in the event of total GNSS failure, we'll fall back onto an INS system. We've performed qualification testing to our own standards for that, which have been seen by the CAA. But as it stands for UAVs, there's no formal qualifications to meet for things like direct INSS performance on a large fixed-wing UAV. So a lot of this is self-qualification that's then presented to the CAA as an allowed process, which we're still supportive of, and it's taken on a case-by-case basis. Generally speaking, that INS system we have, the drift rate sort of 1 kilometre every 45-50 minutes, approximately. And for a lot of our operational use cases, that's an appropriate level of risk mitigation. As I say, it's very much taken on a case-by-case basis at this stage. Does that answer the question? Sort of. You can maybe have a chat afterwards if you want some more detail. Any other questions? Yes.
It's really a question you said at the start about working with the Shared Airspace Council around other airspace users, making sure you're trying to meet other airspace users' needs. So how is all of that aspect of the project going? Are you happy that you're getting good integration with people? Have you had concerns from other airspace users? Because obviously this is normally quite a hot topic around other airspace user forums.
Sure.
I'll hand it to Neil. That one's not working.
So if you can get that one.
I don't think I need it for sample. Well, we've got some members of the Light Aviation Aircraft Association here, and we invited, we're very keen to ensure that we did have other airspace users because projects risk building in silos and not talking to people that overlap the same use of the airspace. There's only one sky, so we have to find ways to cooperate to use it. And that's what this is all about. So I did, in my little intro, pick out the Shared Airspace Council first because I think it's been one of the big successes of this project. That there wasn't really anybody representing all the other airspace users and bringing everybody together so that you could have a common discussion around the table about the various concerns and issues and perspectives on how this is going to go. Because this is only going to end up in one place. At some stage in the future, there's going to be integrated airspace. It could be quite soon, it could be a long way away, depending on how we do it. Shared Airspace Council has been prolific in its activities. I think we've met 14 times now, face to face. We push out bulletins every month or so, and they're 6 or 8 pages of type, update on what's happening in the sector, the discussions that are taking place. We've had presentations from not all, but a lot of the future flight projects. Some people have come along, so we just had Alias recently, talking about Jersey, I think you've seen it on LinkedIn, etc. And they gave us a real deep dive on what they did and what they've achieved in terms of they're a little bit more on the avoid side of DAA, we're a little bit more on the detect side, bringing them together. You can see how you're going to have really, really robust solutions there. We've also got all of the members of the general aviation community, and there's a lot of them, a lot of associations, anything between 12 and 46, according to who you are, representing every model aircraft, gliders, parachutists, hang gliders, you name it. They've all come to the table. They come at their representative level, so the national heads, and it's a duty on those individuals to disseminate what they hear down. So they can't just come and listen to the Alias presentation themselves. They have to report back to their members on what they've heard on what's going on. And we've got each of those associations to talk. If you're a glider pilot, for instance, about where you fly, which is obviously Land's End to John O'Groats across into Europe, what height you fly at, which tends to be as high as you can go to as low as you can go, how you integrate with other airspace users. And, you know, some of these organisations are very needy in terms of the amount of airspace they need to do what they want to do. But there are ways of integrating. What I always do is I look back at what the military did, because the military had to overcome this problem of integrating drones for Iraq and Afghanistan and those sorts of things. And what was a very procedural and segmented process, segmented in time or space, became more and more dynamic as the tools became available. What you've got now with the tools we've been looking at today is you can be really very, very dynamic. You know, we're talking about latencies of 10 milliseconds, a hundredth of a second, which allows you to decision make a lot faster, gives you much more situational awareness because you can see most of what you need on a screen or on multiple screens. And this is all moving apace. There's also a great deal of papers out there. We were discussing them in the NATS ISDG this morning. There's a whole raft of people from the DFT, Future Flight Integration Group, with their action plan, from the FAWIG, from the BVLOS Ops Forum, that are putting papers out, various other groups as well. They're all stating positions on this. The CAA comes out regularly with pieces, either in draft for comments or draft for sandbox participants to work with, etc. So we're actually, all of this project is being built on, and many of the other projects as well, what is actually being directed and guided to us from the regulator. And that's really important because you're staying on a path that's being laid out to you. And the purpose of the Shared Airspace Council is to share all of this, because really, from my perspective, and I've been involved in a few transformation projects in the past, people make it, which is what we see today, people break it as well. So by which I mean, if people don't feel that they're involved, they don't feel that this is something that they should go along with, they find a way to resist it. And it's that resistance to change that slows everything down. So by bringing people in and by having that conversation and giving them early exposure to what we're doing, generally they'll actually say, and I made this very comment this morning, they'll be helpful. They say they've got a lot of knowledge. You know, a lot of these pilots are very, very experienced. And they say, look, this isn't actually a new problem. This is something that's been encountered before. This is how we dealt with it before. This is how we think we should think about it. So they move from being sort of subtle resistance to actually being assistance to the process. So Shared Airspace Council has a pretty open forum, and a lot of its stuff's published, and as we get the website up and running, and the rest of all of the minutes, all of the meetings, a lot of the videos, that sort of thing, published. I encourage people to have a look at it. And if you belong to the associations, reach up and say, where's the information from the last council meeting? What's going on? What's happening with these future flight projects? Have you presented to them? Have you shared our concerns? Because once you share the problems, you can start solving them, and I think that's really happening. So from my perspective, I'm biased, but I think the SSC has been a big success.
Can I have your mic? Oh, is this working now? Okay. Yes. I'm not sure if that one's working.
I'll speak up. It seems to work. Okay, Mike Fox, CAA, EC, Electronic Computing Lead. So you talked a bit about the resilience of the UA if there's a problem with GNSS. Have you done any work on looking at the resilience of EC if there's a problem with GNSS, specifically perhaps jamming rather than spoofing? I know you've looked at spoofing, which looks really good. Have you done any work on specifically jamming, and especially the whole ecosystem really, which relies to a great degree on GNSS?
Yeah, so I think when it comes to GNSS, it's a big problem. It's if you're relying on ADSB. Ultimately, ADSB is using GNSS for the positioning. Now, obviously, spoofing is another matter. So if you spoof GNSS, it generally has quite a fairly local effect. So what you can find is that if you're using if you're using a single sensor, then it's much more susceptible to spoofing because you're not listening to the view of lots of sensors. So if you've got spoofing in a specific area, these sensors over here might be being spoofed, but these ones won't. So it gives you a chance to actually detect it and then do something about it. We haven't gone through that process of detecting it and resolving that, but certainly from a theoretical perspective, it's a lot more robust to it than a single sensor approach. I think our kind of view on this is, if you hear the same thing from 10 different people, you tend to start believing it. If you hear it from one person, you're like, you wouldn't bet your house on it. So our view is lots of sensors from different areas, from different people especially, gives you a very, very high level of confidence in the data that you're receiving. Now, if people are spoofing GNSS over a large, very, very large area, I think it would be very hard to do, first of all. And secondly, you kind of sometimes have to just accept that someone drops a nuke on us, we're all in trouble. So, there's certain risks we have to deal with and certain risks that we kind of just have to hold our hands up and say, yeah. But I think, hopefully in the future some of these issues will be resolved by technology. I think there are ways to get around it. Certainly, I know Cranfield have got a big piece of work on position navigation and timing. I think they're one of the first in the UK to actually have synchronized atomic clocks, I believe. And we have had thoughts about potentially integrating with that, using a different time synchronization rather than the GNSS, because basically ADS-B and Mode S is working off GNSS time synchronization. So it's using the nanosecond timing of the reception of these signals to be able to assure the position of the aircraft. Now, if you're obviously if you're losing that GNSS, then you need a different way to be able to do that. And if you had positional timing, and then you had the signals from the aircraft, if you had the time synchronization from this separate system and the signals from the aircraft, albeit with incorrect GPS positions on them, then you would be able to multilaterate those positions. So I think that could be a potential solution.
Glad you think about it.
Thanks.
Yeah, I can add that from the practical standpoint, also in this project phase, but in the next project phase, it can be included and it can be tested. We are in touch with some of this kind of counter-UAS equipment, and in the next phase, it can be included, it can be tested, and some of the measures can be implemented, as James said. So we are more than capable.
It's worth also mentioning, just on that we have to also remember that failure of a detect and avoid system isn't inherently a safety critical failure. So losing a fail-safe system, or a system that's designed to stop you from crashing into other aircraft, there are other systems that will help to mitigate airspace risk as well. But losing your detect and avoid system doesn't necessarily mean you will actually crash into something. It's actually very hard to hit things, believe it or not. If you ever go to these remote control conventions where they try and smash planes into each other, it's actually quite difficult to fly planes into each other, albeit it can happen. So we do need to mitigate the risk of it, but what I'm saying is just trying to highlight the additional point that it's not necessarily means that every aircraft out there is going to crash. Anyone else? No more hands. Okay, well, we'll give you 3 minutes back of your time. I can't believe we actually ran this thing on time. But apologies, it's probably my fault from earlier. So, but I'd just like to thank the team for all their efforts. They've put in a huge amount of work over the last, 24 months, and in particular the last 4 weeks has been very, very tough. I know probably a few of us might go to the pub after this and wind down. So, but thanks everyone, especially everyone here, also for taking the time to come to Cranfield. It's not just down the road from a lot of you. I'm sure some of you have had to travel for a few hours to get here. So thanks everyone for coming and listening to us speak to you for 2.5 hours. So hope you spend the next hour to go and network, meet some more people. If anyone wants to chat to any of the team, I think most of us will stay around for a bit longer. So yeah, please do enjoy yourselves until about 5 o'clock, at which they'll probably chuck you out. But thanks everyone for coming. Cheers.